already looked at the special continuous random variables, and as usual, I will always start with a brief review of our material, at least the things that you should have nailed down in order for us to continue with the normal random variables. So since we already know a normal random variable can be defined based on its mean, mu, and its standard deviation. In this case, sorry, its variance, which is sigma to squared. So if I were to write down x follows the normal distribution, I would need to put in the parentheses the parameters that define it, which is the mean and the variance. So what we need to know is that these values of the mean and the variance can differ, right? Because as you know, the normal random variable or a normal distribution can have various shapes. It could be centered at 10 as such. It could also be centered at 15, then we have a different mean. And it could also have a different standard deviation or variance, and such it would be a little thicker or a little wider. So instead of actually computing every single possibility when we define a normal random variable, it's a little easier for us to instead use a standardized version of normal, which is our standard normal variables. So remember when we did z-scores, we're also standardizing distributions. So if we want to be able to compare two different things with different distributions, we can map it to the same distribution in order for us to be able to compare them fairly. And the same thing goes here. So instead of computing the different CDFs and PDFs for every single possible normal variable, we can instead convert all of these normal variables into a standard normal random variable, which is denoted here using z, which follows a normal distribution. So it's the same thing. You write it the same way. It's normal with a mean of 0 and a variance of 1. So the notation is the same. It's only that the parameters of mean and variance are fixed at 0 and 1. So since we already transformed all of our normal variables to the same domain, you can say, to the same measurement. So now one of the advantages that we have is that we can compute everything in the same manner with the same equation, which is our CDF. So the CDF, as we already described last week, is as follows. You are computing the integral between certain limits of the PDF f here. But since we know it is a standard normal distribution or a standard normal variable, we now have a new symbol phi. So this symbol phi can be used as the CDF. So instead of writing the large f, don't forget small f is PDF, large f is CDF, I can just use pi instead. And this symbol is what you can is used when you are considering a standard normal random variable. So it basically means the same as what fz would mean. So fz, what I mean by fz is the large f. So it basically means the same thing as fz. As you remember, this is the CDF, and we recall that the CDF is the probability of a random variable having a value up to this certain value here. So as it is defined, the phi, the pi of z equals the large f of z equals the probability that our random variable has a value up until z. So up until z. So what happens is basically, since we already know the shape of a normal random variable, and we already know that this must be centered at 0 because it's standardized, and the standard distribution is, the standard deviation or the variance will always be 1, then we know that this graph here of n01 would be valid for any normal random variable that has already been converted to a standard normal distribution. So when I'm considering the pi of z, that means z there, I want to compute the probability of my random variable having any value up until z, so any value lower than z. And how can I compute it? Well, I could compute the area under the curve exactly as mentioned here using the integral, or we can use the z table. We can use the z table because it's standardized. It'll always be centered at 1. It'll always have a standard deviation. Sorry, it's always centered at 0, and it'll always have the standard deviation of 1. No matter where you started off with, whatever mean or whatever sigma you started off with, you convert it first to n01, and then the table is valid for everything. So since the normal distribution has some special properties such as symmetry, and also the sum of all probabilities must equal to 1, these are the rules that we have learned prior to this class. Then if I were to compute the other side, so not less than up to, but larger than, I can also compute it by either using 1 minus, then I can use 1 minus the left-hand side, or I could just assume it to be symmetric, and I could compute the probability of it being up until negative z instead. We covered this in detail last week. So due to the sum equaling 1, as well as the symmetric property, we can use that same table for computing left-hand side and right-hand side. So to do that, we start with any normal random variable here with any mu and any sigma, and then we need to convert it using the z-score equation here into n01. And thus we can then compute using the pi alias the table. We can use the table to compute probabilities up to. So to illustrate this, I'm going to show a different example, and we're going to look at what happens if we have more than one random variable. So like, for example, we have x that follows a normal distribution. We have y that follows another normal random distributions. So if we know that we have distributions that we know for sure follow a normal distribution, we then can combine them into new normal distributions. So here, for example, on our left-hand side, we have linear combinations or linear functions of normal RVs. So if we know that A and B are constants, then we know that if the second random variable y is a linear combination of x using these two constants, then if I don't know the parameters of y, it doesn't matter because I can derive the parameters of y based on the parameters of x. So usually you will be given in the question like, oh, if we know that y is a linear combination of x and so on and so forth. Next, we also have on the right-hand side, the sum of two independent normal RVs. So if I know that I have x1 and x2, and I know that these two random variables are both normal and they are both independent from one another, then I know that I could compute that y would be, if I would like to add them up, x1 plus x2. And thus I can then compute the parameters of y. See, it's still the same. It's still a normal distribution, but we have updated parameters here. Sorry, we have updated parameters here. So on the left-hand side is a linear function. On the right-hand side, it is a summation of two independent normal RVs. Next, we also have linear combinations of independent normal RVs. I know that that if I have x1 and x2, or here it's generalized to xi, so x1 until xn. If I know that y is a linear combination of x, I can also derive the parameters of y using these functions here. So if I only had one in this case, if I only had, sorry, not one, if I only had y was a1 x1 plus a2 x2, for example, then I would know that this would follow a normal distribution. B is 0. In this case, I have no B. And this would be the sum of A1 mu 1 and A2 mu 2. Okay, note here that if I don't even have an A, say I only have y equals x1 plus x2 here, note here that what happens is, wait, now I have two x's. Shouldn't this be a1 plus a2? Because the means are ignored because I don't need a, sorry, mu1 and mu2, sorry, because the a's are 1. And you see that you go exactly back to this equation here, which was x1 plus x2. And on our right hand side, we have averaging independent normal RVs. And note here that if we have A and B are constant, I can then compute X is average of multiple Xi's in this case. Then I can compute the mean does not change, but the standard deviation must be divided by the number of random variables involved. So to illustrate these possible combinations better, I'm going to use some examples. So here is our first question. The yearly precipitation in Los Angeles, we know, is a normal random variable with a blah, 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 blah. Don't forget that first we need to define our random variables. This is an important point. I know that X follows a normal distribution with a mean of 12.08. Apologize my handwriting, I'm using my mouse. And the standard deviation of 3.1 inches. When we are defining our random variable, we need to write it in terms of variance. Okay, so this is the first step. So here it's a little bit unique because it says yearly precipitation. That means we have year 1, year 2, year 3, and so forth. So I'm going to add a little subscript here, xi. So I know at a year I, at any given year, it will follow a normal distribution as follows. And now we want to know, find the probability that the total precipitation, total, it's a summation, during the next 2 years will exceed 25 inches. So here we have x1, which I know follows this distribution. I'm not going to write it down, and just copy this area here. And we also know that x2 will also follow the same distribution. Thus, if we wanted to compute x1 plus x2, we also know that x1 plus x2 will follow a normal distribution. However, as we've seen here, it will follow a normal distribution with a little different parameters. So here it says to sum up the mu and to sum up the variance. So in other words, this would be 24.16. And this one is, I haven't squared it. So it should be something like 2 times 3.1 squared. And we also know that this particular random variable is also normal. So we can compute whatever it is that's asked of us, using our normal variable knowledge. So what is asked here? I'm going to give a divider here. So what's the probability that x1 plus x2, this is one random variable, in the next 2 years will exceed 25 inches? Okay, what is the probability that that will happen? So don't forget, we need to first convert it into a standard normal random variable. So we would need to x1 plus x2 minus mu divided by that, and 25 minus 24, 16 divided by, we need to compute this first, I guess. I think I've already computed it somewhere. Let me go check my key. Okay, so here we have, apparently this is 19.22 here. So I can write here that it should be the square root of 19.22. And then you can continue on with that with our phi, and I already have the key here so we can see it in better handwriting. So note here that after that, we just use the same concepts that we did previously when we only had one random variable. It's more or less the exact same thing, only that we need to first define the correct distribution of the combination, which is also normal, and then we just follow the same steps that we have always followed when we're solving a normal distribution problem. So then I end up with the probability of z being over that number, and you can check your z table. You can either, you have two choices here. You can either use pi minus 1916 or 1 minus pi 0.1916. So these two options are the exact same thing that we have covered all this time with only one random variable. Okay, so up until now, I gave you an example of how these normal random variables can be combined if there's more than one, and we know that the combination follows one of the four categories that we presented previously. So now I have a discussion point for you. I'm going to stop and pause as well. So in this example, I'm going to illustrate the same thing. So here we have a machine that produces paper with the thickness of the paper following a normal distribution. So here we, as usual, we should denote all of our variables correctly. So for example, if I have the width of W denotes the thickness of paper, and this W, I know it will follow the normal distribution with 0.1 and, oops, eraser, 0.1 and standard deviation of 0.06, 0.06, 0.006. There are two zeros there, sorry, to the power of 2. Please think about the questions A and questions B. What is different about these two problems? The first one is state the distribution of the total thickness of 8 randomly selected sheets of paper. So you have 8 sheets of paper. You're taking 8 of them. I know that I need to sum up 8 random variables. I need to sum up W's, right? So this is one W that I have here. On the B part, the B question, it says that if I have one sheet of paper, a single sheet of paper, oh, this is, sorry, grammatically incorrect. A single sheet of paper is folded 3 times. So I fold it 3 times. That means it has 8 levels, right? 8 layers. So oh, I don't have paper around here. So do I have paper here? It isn't, because it is a single piece of paper. Not only is it the same distribution of thickness, it's also the exact same thing. It's the exact same object. It's the exact same variable. It's the exact same variable. And it is dependent of each other. So this particular part, like this layer here, this layer here from one of the foldings will depend on the other one, because this is one single sheet of paper. You can't really see it. Yeah, it's one single sheet of paper. So this is a good, I believe this is a good illustration in order for us to understand which one is dependent and which one is independent, and which one can we use, when can we use a summation of multiple normal random variables, and when we can use the linear combination. So I could just do, this is a linear combination, right? Which is AW plus B, where B is 0 and A is 8. So these two problems, A and B here, are very different, although in the end, you are computing the exact same thing. So keep in mind that in that previous example, you need to think about the independence of the random variable as well as the individual distribution. So other than that, the normal random variable is also quite useful for us to compute other stuff. Like, remember when we try to approximate the binomial distribution? We already tried to approximate it using Poisson, right? So it is possible to approximate the binomial distribution using a Poisson random variable if it fulfills some certain criteria. Additionally, the binomial random variable can also be approximated by the normal random variable. So instead of x being a binomial distribution with the parameters n and p, I can instead describe it as a normal distribution. The mean is n times p, and so forth. And once again, we have some rules of thumb that we can follow as to when we can use these these approximations, sorry. And it says basically when NP is larger and equal to 5, and the approximated variance is also larger or equal to 5. Once again, keep in mind that this is a rule of thumb, not something absolutely correct. So please take this with a grain of salt. But we have a small issue here. Remember that a binomial random variable was a discrete random variable. But instead, the normal distribution is continuous. So we need to account for that, and we need a little correction term to account for the continuous normal random variable. So when I say you can approximate it as follows, so NP, then I can just multiply it together. You need to add a 0.5 correction term when you are computing the probabilities. So it's not as simple as just computing NP, but you also need to correct that. So note here that when you are going less than, so here is less than, you need to add on 0.5. But if you're computing less than without an equal, then you need to correct with minus 0.5. And on the other way around as well, if you want to compute the right-hand side or larger than, then you need to correct it with a 0.5. Basically, if you are doing an equals, you need to correct for an additional 0.5 in the opposite direction. So here is less than, right? So you're from the left-hand side, less than, you're coming in from the left-hand side. And at the point of where you're having your limit, you need to add plus 0.5. Same goes for when you are computing the larger than and equals, because you're going from that side, right? And then you need to account for an additional 0.5, but to that direction, to the left. That means minus, right? If you're going to the left. So you need to correct it, giving a little extra when you have equals. However, when you're using not equals, only less than, you need to correct it with a minus correction term as well. So as an example here, you can see that if we have a random variable x that is following this binomial distribution, I could approximate it using this normal random variable. So instead of B16 0.5, I can use YN84. And see here that if I were to compute it, I could compute it using either way. I could use the binomial information, or I could also use the normal approximation. Note here that instead of 8 and 11, I need the correction terms, right? So since in this case, it equals and equals, then I need to go a little bit left, 7.5, and I need to go a little bit right to 11.5 to account for this correction term. And as you can see, it's not an exact computation. It's not going to give you an exact one, but it is a good approximation. This comes in quite handy when you have questions such as this one. So if I use a binomial random variable in this case, I would end up with, sorry, let's write that down using the equation of binomial. It would be something like PMF equals something like that. And this would be like 400 and 190. This is a combination, right? So it's quite difficult to do a manual calculation of 400 factorial. However, these days you do have your helpers. You can use your combination calculators. However, it could, in the case that you don't have access to this calculator, you can approximate it using a normal random variable instead, which is a lot more manageable. The computation is a lot more manageable. As many times I have already mentioned by now, the normal distribution is the basis of a lot of things that occur naturally in the world. So it is a safe assumption usually that when you have any data, it will follow the normal distribution. However, obviously, it's not always perfectly normal with a perfect centered and a symmetric tails. It's not always the case. So due to the properties of the normal distribution, we can derive some other some other distributions that are defined based on the normal distribution. So the first one is the chi-square distribution. So if you have n standard normal variables, note here that they are standard normal, not only normal, so they're already standardized to 0 and 1, then a combination of these independent standard normal variables like this can be defined as a chi-square distribution with n degrees of freedom. So if you have n standard normal variables, that means you have n degrees of freedom. You can also use this notation. X follows a chi-square distribution with a certain degree of freedom. So if your degree of freedom is 8, then you can write it as X follows a chi-square. This is like not a normal X, it's a curly X with a degree of freedom of 8. And this is just squared. And since it is a combination of standard normal variables, you still end up with quite simple expectation mean, which is n, and a variance as 2n. So what I want you to take out of it is what exactly does the chi-square distribution mean? So I'm going to draw you back to the initial Z alpha notation that we looked at last week. So if I recall correctly, was it Alexander or Jonathan? I forgot, one of you said that, so basically the Z alpha is the opposite of looking up the Z table. And actually that is exactly correct. So when I say Z 0.05, that means from a normal, right? This is from a normal. So from a normal distribution, where do I draw that line so that the right-hand side is 0.05 of my population? So where do I draw the line so that 0.05 parts of my population will fall on the right-hand side? So bring that thought process into the chi-square distribution. So if an X is a chi-square random variable with n degrees of freedom, then for any alpha, this is your alpha here, the quantity of this chi-square distribution, so any alpha So here, let's say 0.01, for example, with a degree of freedom. For example, here the degree of freedom is 8. Then what this symbol means, this symbol over here means, is where can I draw this line? Where can I draw this line so that I know that this area under the curve on the right-hand side would correspond to 0.01 parts of my population. So it's useful when we would like to know what is, so let's give an illustration. So I need to legalize some new drug. And in order for me to get this drug legalized, I need to say that it is safe for 99.9% of the population. So 99.9% would be then 0.99, right? It has to be safe for the 0.99 parts of the population. So I have this leeway. So I need to know at what point is the limit in which I cannot go any further, for example. So I know that in this dosage, it's fine, this dosage is fine, this dosage is fine, this is for 0.99 of the population. But when I go here, okay, this is your limit. If you go any further, more than 0.99 of your population will be on your left-hand side. Here is where this notation will fall. It will come in handy because in that case, then I need to know like 0.01 here, right? So I need to know where do I need to draw the line so that 0.01 of the parts of the population will be safe on the right-hand side. That is just an illustration though. So the basic points that I would like you to take away from the chi-square distribution is, first of all, based on the degree of freedom, how many standard normal variables are involved in this. The first thing is that this DOF will determine the shape and the skewness of the graph. So I know, like, for example, the degree of freedom is 8. Let's change it to, it's 10. And I know that if it's 10, oh, the shape is something like that. Next, if I want to know, oh, where is the line where I need to draw so that the proportion of data, alpha, would fall into the right-hand side. So in other words, what's the probability that the X or the random variable would be larger than this limit, this line here? So this is called a critical point. Ooh, shouldn't make it double, sorry. Let's delete that. So this is also called the critical point, which is the point at which alpha parts, I'll generalize it. For this, I know that the degrees of freedom, for example, is 10. So for this particular graph of the chi-square, where the degrees of freedom are 10, I know that this is the critical point at which alpha parts of the population will fall on the right-hand side. And thus we can compute using this notation. We also have the same concept using the same type of, table. And if I were to ask you, find the X, the chi-square, critical value. So here I'm asking you to find the critical value of a chi-square distribution with an alpha of 0.05 and degrees of freedom of 15. So you need to look it up. Where are my degrees of freedom? It's 15, it's over here. And it's 0.05, which is this is your alpha here, 0.05, it's over here. That means this is your critical point, which is 24.996. And based on what we already talked about just now, what this actually means is that, oh, I have a chi-square distribution with 15 degrees of freedom. Let's assume that 15 degrees of freedom looks like that. It's not, it's just, I'm just making a graph, okay? And I want to know that in this case of 15 degrees of freedom, where can I draw my line so that 0.05 parts of my population will be found on the right-hand side. So this area here. And in this particular case, that means that this value is 24.996. Okay. Derivation. Why do I say that this is the most important derivation? Because it still has the same symmetric property and the same centered at zero property as the normal distribution. So as you see here, that the T density is symmetric at zero. So that's the same thing as normal. And as the n becomes larger, it becomes more and more like standard normal density. So although I said that most things in the world, most data points in the world that fall into will fall into the category of normal distribution. However, sometimes we don't have enough data points to assume that the distribution is normal. So in that case, we very often use the T distribution instead because it's symmetric. It looks the same as the normal distribution. However, it accounts for the error that may occur if you don't have enough data points. In other words, you can also say that it is the chi-square, a chi-square variable divided by how many data points that you have. So there are some important properties of the T distribution. See that they have thicker tails than the normal distribution, and that indicates greater variability. And this will be used, I'm going to write this here, when you do not know for sure that the population is normal. So when you have a series of data, you collect data, you have their data. As I said, it's a safe bet to assume that it would follow the normal distribution. But it would also be very premature if you just assume that everything was normal. So instead of assuming that, oh, this is a normal distribution, you can more safely assume that it would follow a T distribution, which is still a derivation of normal. It follows the same properties as normal. However, it will not have you, but that way you don't overclaim your data. So in this case, please note that in 2 weeks or 3 weeks, when we go into hypothesis testing, you will have to consider your data. Is it normal or not? If you know for sure it is normal, you can use the normal distribution. If you don't know it's normal for sure, like for example, it's not given to you in the problem, then to be safe, use the T distribution instead. So this is just a mathematical derivation of it. And as you can see, it's exactly the same as the normal distribution. The way we compute probabilities is exactly the same. So if I'm computing, this is the critical point here with a certain alpha, like how much parts of the population is on the right-hand side. It also is the same for the left-hand side due to the symmetrical property. And I can also do 1 minus, just like what we did in the normal distribution. And I can do the probability less than the negative one, also just like the normal distribution. So we're going to look at it both ways here. So first, note that the chi-square distribution as well as the T distribution gives you the opposite of the z-score. So the z-table, sorry. So when last week, Joe or Alexander, I forgot, I'm really sorry, please say it if it was you, mentioned that the z alpha is looking up the table opposite. So this way, in the t distribution and the chi-square distribution, it's not opposite anymore, because instead of looking at the proportion, you're trying to find the line at which you draw the line. So here, find t 0.025, degrees of freedom 9. So you know that, oh, I know the degrees of freedom. I know the shape of the graph. It should be somewhere here. And I want to know, where do I, so here's the, oh, should use red, but so here's our shape. This is our t distribution. And I know that it has 9 degrees of freedom. So its shape is something like that, assuming. And I want to know, where do I need to draw the line so that I know for sure that 0.025 of my population is on the right-hand side. So I want to know that 0.025 parts of my population is on the right-hand side. Where do I draw my line? So here it's 9 and 0.2025 here. So it's somewhere there. So I know that I need to draw my line at this point, which is 2.262. So the probability, or in other words, the probability that T9 is larger than 2.262 is equal to 0.025, the probability here on the right-hand side. So from this part here, you probably can already, you probably have an inkling or a feeling how we can solve the second part. So now I know I'm trying to compute the opposite. What's the probability that my T with a DOF of 12 is less and equal to 1.4? Okay, so what's this probability? So let's draw what we're trying to do. So, okay, here, I know that I'm drawing my line here at 1.4. Okay, I know it's the opposite. I'm drawing my line at 1.4. So I want to know what's the probability it's less than that. In other words, I'm trying to compute the less than, this area here. I can do that by trying to find this alpha, and then I can compute 1 minus. So I'm doing the other way around. So let's try to find an entry that is more or less 0.4. I can't find an exact one. However, I can, oh, sorry, what's my degrees of freedom? 12. So I have to look at this one here. This one there. It is this one there. So I know I need to find an entry that is 1.4. I don't have one, but I know it should be somewhere between this one and that one. So this is 1.3, this is 1.7. I know that it has to be somewhere in here. So in other words, it has to be between 0.05 and 0.1. So this alpha must be somewhere between 0.05 to 0.1. That means this remaining part here, this remainder part must be somewhere between 0.9 to 0.95. And this is the answer. So it's true that the T distribution table on its own is very difficult if you want to compute the probability. But lastly, we have the F distribution. So again, it is again a combination from a chi-square divided by n, chi-square divided by m. Remember that chi-square divided by n, this was t, so these are two t distributions. And this would be said to have an F distribution with n and m degrees of freedom. So basically what you have here is, if you are trying to compute something, you need to try to compute the F distribution. You are given the alpha, and you are also given the m, and you are also given the n. And I did not screenshot the F table here because it has multiple pages. Please look up on Scale, because I have re-uploaded the F table, because previously it was only one page that I uploaded. It should have more than one. So in this particular example, where it says find your alpha is 0.9 and so far and so on and so forth. You can then look it up using your F table where different alphas are available. Here's alpha 0.1, here is alpha 0.05, and here is alpha 0.01. Note that not all alphas are available. Then you can look up based on the N, the first degree of freedom, and M, which is the second degree of freedom, and then you can find the critical point. Once again, chi-square, T, and F distributions all are, the tables give you the critical point, not the probabilities. It's the exact opposite of what the Z table is giving you.